There is a lot of confusion about tails. Heavy tails, fat tails, long tails, and so on are used as synonyms. Unfortunately, this is not correct from a statistical point of view. A heavy tail is a particular type of tail which is different from a fat tail, which is different from a long tail. What I want to try to do is to give a taxonomy of tails, a bestiary of tails, in which we distinguish the different types of tails. We will see that actually they are connected. So we can for sure say that a fat tail is a heavy tail, but a heavy tail is not a fat tail. So let's try to give a clear definition of the different tails. As we shall see, every definition is just linked to one specific requirement for the random variable that we are considering, that we are studying, and whose tail is of interest for us. In classifying tails, we will start from the most general class, that is the class of heavy-tailed distributions, and we will zoom in until we reach the class of fat-tailed distributions. Now, what I can already tell you is that the class of fat-tailed distributions is included in the bigger class of heavy-tailed distributions. So if a distribution is fat-tailed, it is also heavy-tailed. But the opposite is not necessarily true. For example, the log-normal distribution is a heavy-tailed distribution, but not a fat-tailed distribution. In order to define heavy tails, we need a benchmark. So we need a tail that we consider as a benchmark such that we can define heavier and lighter with respect to the benchmark. Now, the benchmark for us is the exponential distribution. Now, I will not enter into the details of why we choose the exponential distribution. There are actually many different technical details for doing that, but we would need an entire course to consider all the technical details. Let's say that at the end of the day, if you want, they are all connected to the behavior of the moment generating function, as we shall see in a minute. But actually, it is a little bit more subtle. For example, using pseudo-analysis, we can find that there are very interesting connections in the exponential distribution that we exploit then when we define heavy and light tail distributions, but again, we skip that part. In any case, if you recall what we have just said about the generalized extreme value distribution and the generalized Pareto distribution, also there the exponential plays an important role. In the case of the generalized extreme value distribution, the exponential tail is essentially the tail that is representative of the Gumbel class. And in the generalized Pareto distribution, the exponential case is the case that we get for xi equal to 0. So you can see that actually the exponential is a very important distribution in extreme value theory. So let's say that we consider an exponential tail. So we are considering an exponential random variable, which is a random variable that you for sure know, and we consider the survival function of an exponential random variable. Now, an exponential random variable of parameter lambda has a survival function as the one that you see on your screen. So let's consider a non-negative random variable. As I told you several times, if we consider random variables that can be both positive and negative, it is just sufficient to look at the two tails independently, and then all our definitions are perfectly okay. But let's just focus on the non-negative part, okay, just to simplify. We say that a random variable is heavy-tailed if its survival function decays slower than the survival function of an exponential random variable. That is our benchmark. It means that if I take the ratio of my survival function and the survival function of an exponential random variable, then this ratio, if I zoom in into the tail, so if I take my value small x growing to plus infinity, then this ratio explodes to plus infinity. So what we are saying is that a distribution is heavy-tailed if the mass it assigns to a tail event is larger than the mass an exponential random variable would assign to the same event. Conversely, a random variable is light-tailed if its survival function decays as fast as the exponential survival function or even faster. From your basic courses in probability and statistics, you for sure remember the moment generating function of a random variable x, which is defined as you see on your screen. We know that when the moment generating function is well defined, we can use that to characterize the moments of a random variable. We know that it is connected to the characteristic function, and when the moment generating function is correctly defined, it actually characterizes a distribution. So if we know the moment generating function, we can always try to recover the distribution behind. Now, what I want to show you is that actually, when we give the definition of heavy-tailed distribution, we are saying something very important about the moment generating function of the random variable we are considering. In fact, if we go back to the definition of heavy-tailed random variable that we just gave, we can easily see the connection with the moment generating function of the random variable we are considering. It is just sufficient to take the exponential survival function that we have at the denominator and take it to the numerator by just changing the sign of lambda. Now what happens if I consider the argument of my limit, which is e to the power lambda x times the survival function of x? Now it's easy to see that since this quantity goes to plus infinity, we are essentially saying that the moment generating function of our random variable x is infinite for all lambdas larger than 0. So for what concerns heavy-tailed random variable, the moment generating function is no longer the useful object that tells us, for example, how the moments of the random variable behave, the object that we can use to characterize the random variable, the object that is the basis for very important statistical relations like the Chernoff bounds. So, while for a light-tailed random variable the moment generating function is an extremely useful object that we can use to play with the random variable, for a heavy-tailed random variable the moment generating function, being always infinite for every lambda larger than 0, essentially is useless. It means that for a heavy-tailed random variable we have to think about other tools, so we have to use other instruments. And also the fact that the moment generating function is infinite tells us that when we play with heavy-tailed random variables, we have to be careful in dealing with their moments. Famous examples of heavy-tailed distributions are the Pareto and the log normal, and many of their transformations. In the class of light-tailed distributions, conversely, we find necessarily the exponential, which is our benchmark, and another fundamental distribution in statistics, like the normal distribution. There are then distributions that can be in both classes depending on their parameters. A very important example is the Weibull distribution. I would like to conclude the discourse about heavy-tailed and light-tailed random variables by letting you notice an important connection between the two classes. It is a connection that, for the moment, we leave there, but it can be very useful in practice. Now, we know that a heavy tail distribution and a light tail distributions are different animals, and we know that, for example, in the light tail class, we can use the moment generating function with all the nice properties. We can build concentration inequalities, we can play with the Chernoff bands, we can compute all the moments using the moment generating function, while this is not true for a heavy tail distribution. Yet, there is a very nice connection. Now, you know that the log-normal distribution, which is an example of heavy-tailed distribution, can be obtained by an operation that we call exponentiation of a normal random variable, where the normal is light-tailed. But it is very nice to observe that also the Pareto is the result of a similar operation. Indeed, the Pareto distribution is the result of an exponentiation of what? Of an exponential random variable. Okay, we have defined heavy-tailed, and we are now ready to introduce long tails. Long tails are a class of tails that is included within heavy tails. So a long-tailed random variable is also heavy-tailed, but the opposite is not necessarily true. So we can always consider random variables that are heavy-tailed but not long-tailed. Now, in order to define the long-tailed class of random variables, we need to introduce an extra requirement with respect to the requirement about the moment generating function or the behavior of the survival function. This requirement is what we call the explosion principle. According to the explosion principle, if a very large event manifests itself, then the probability that an even larger event will happen approaches 1. Now, in other words, what we are saying is that if we observe in our portfolio a very large loss, then the probability that an even larger will happen sooner or later approaches 1. So you can imagine that it is quite stupid, it is a blatant error to assume that the maximum loss we have observed so far is actually an upper bound for the losses of our portfolio. And any model that assumes the partial maximum we have observed so far as an upper bound, or that assumes the probability of larger losses to be negligible, is blatantly wrong and dangerous for us. And unfortunately, most of the phenomena that generate losses in a financial portfolio are long-tailed. Okay, so it is not very clever to assume that the probability of very large losses is negligible so that we can set it to 0 and ignore that, because otherwise, at a certain point, the Lehman Brothers situation manifests itself and we say, oh, that was not possible. Yeah, it was not possible according to your model. Now, it is very important to understand that the explosion principle tells us that the probability of observing an even larger phenomenon, given that we have observed a very high level, approaches to 1, but it does not tell us when it will happen. Okay, this is very important. It's not that if a very large loss manifests itself today, tomorrow we necessarily will observe a larger one. When combining extreme value theory and time series, we will see that most of the time extreme events tend to cluster, and in fact we have to impose some conditions in order to treat them, the so-called deconditions, but the fact that they tend to cluster does not mean that they will always cluster. Okay, so the long tail random variable that follows the explosion principle tells us that at a certain point we will observe an extreme which is more extreme than the extremes we have observed so far, but not necessarily the next day or 2 days after. Okay, time is not included in this framework. Nevertheless, it is very important to remember the explosion principle because of its strong implications in modeling. So every random variable that satisfies the explosion principle is essentially a long-tailed random variable. Heavy-tailed and long-tailed random variables are extremely appealing and interesting from a theoretical and a probabilistic point of view. But their use in practice can be a little bit cumbersome because verifying, for example, the conditions for being heavy-tailed or long-tailed is not always easy from a practical point of view with data. So what we can do is to further restrict our attention to a smaller class of random variables, which is included in the long-tailed and so in the heavy-tailed classes. This class of random variables is what we call the subexponential random variables. So we focus our attention now on the so-called subexponential tails. Every random variable that is subexponential is also long-tailed and heavy-tailed. But again, a random variable can be heavy-tailed but not long-tailed. It can be heavy-tailed but not subexponential tailed. And again, it can be long-tailed but not subexponential tailed. So what we know is that if we can verify the principle that is behind the subexponential class, then automatically we know that the random variable is also long-tailed and heavy-tailed. But if we know that a random variable is long-tailed, it is not necessarily subexponential. Now, subexponentiality is defined in terms of a second principle that is very reasonable from a practical point of view, as we shall see, for example, in dealing with credit losses or operational losses. And this principle is what we call the one-shot or the catastrophe principle. If you want, you can restate the catastrophe principle as the winner takes all. So let's consider a collection of IAD random variables, and let's define the partial sum Sn and the partial maximum Mn. Now, the catastrophe principle tells us that the probability that the partial sum Sn will be larger than a given large value x is approximately the probability that the partial maximum Mn will be larger than the same large value x. It means that if the random variable we are considering is subexponential, at a certain point the behavior of the partial sum will be dominated by one big player, so by the partial maximum. So it means that if I have a portfolio and I consider the losses that are generated by this portfolio, the total loss of the portfolio is essentially given by one single big loss, and all the other losses are just noise around this big, large loss. So according to the catastrophe principle, if I consider my collection of random variables, the maximum is what really matters. That's why extreme value theory that deals with maxima becomes a fundamental part of the approach for the correct modeling of large losses, large profits, and all the extreme events we might be interested in. Why? Because one single event plays the role, wins everything, the winner takes all. The subexponential class is extremely useful in applications. It is a very rich class of distributions that allows us to model all the phenomena we might be interested in QRM. Within the subexponential class, we find, in fact, distributions like the Pareto and the log normal. An interesting characteristic of the subexponential class with respect to the long-tailed class and the heavy-tailed class is that for the subexponential class we can rely on many very useful heuristics. And we have very useful graphical tools that we can use to quickly understand if a random variable is subexponential or not. Within the class of subexponential random variables and tails, we finally find the class of fat tails. As we have already said, a fat-tailed random variable is nothing more than a random variable that belongs to the maximum domain of attraction of a Frechet distribution. In other words, it is a random variable whose survival function is regularly varying. That is to say, it can be expressed as the product of two components, a power law decay and a slowly varying function, which is that element that in the limit vanishes and just leaves the power law decay, x to the minus alpha, or x to the minus 1 over xi, depending on the parameterization you want to use. Fat-tails random variables constitute a large family of random variables extremely useful in risk management to deal with phenomena like credit risk, market risk, and operational risk. But what I want to stress is that in reality, the most useful and rich class is the one of subexponential random variables. Fat-tailed random variables are included in the subexponential class, and they have very nice extra properties with respect to the subexponential class. For example, they have a limit scale invariance property that we will use in some of the graphical tools that we will consider, and that can also be exploited in some of the analytical tools. But in any case, what it is important to stress is that a fat-tailed random variable is necessarily subexponential, long, and heavy-tailed. The introduction of the fat-tailed class finally separates two friends, the Pareto and the log-normal random variables, that become enemies. Why that? Because a Pareto is fat-tailed, while a log-normal is not. They are both subexponential, but log-normal is not fat-tailed. In any case, this is something that you should already know if you remember what we said after discussing the Fisher-Tippett theorem and when we were discussing the generalized eigenvalue distribution. What we know is that the Pareto distribution is in the maximum domain of attraction of a Frechet because of the particular nature of its survival function, which is essentially decaying as a power law, while the log-normal is in the maximum domain of attraction of a Gumbel distribution, together with the normal distribution and the exponential distribution. Therefore, the behavior of the maxima generated by a log-normally distributed random variable is completely different from the behavior of the maxima generated by a Pareto distributed random variable. But here we really see the tricky nature of the log-normal. In fact, despite being in the Gumbel class, so from the GEV point of view, log-normal behaves like a normal, behaves like an exponential, and not as a Pareto that is in the Frechet class. Nevertheless, the log-normal can generate very strange tail behaviors. And in fact, the log-normal is subexponential. It is long and it is heavy-tailed, while the exponential and the normal that are still in the Gumbel class are light-tailed. We will see in applications that very often, using graphical tools, at least if you just rely on a few graphical tools, it is very difficult to distinguish between a Pareto and a log-normal. So you might need a combination of graphical tools that nevertheless is always what I suggest. Never use one plot or two plots, use a collection of plots, and even more, we might actually perform some tests to really distinguish between a Pareto and a log-normal. We will actually see that there are very important differences between a Pareto random variable and a log-normal random variable, even if when in data it is difficult to distinguish them. For example, the Pareto random variable might not have all moments finite, so some of the moments of a Pareto random variable might not exist, as we will say. For what concerns a log-normal random variable, on the contrary, all moments always exist. Now, in the last slide that you find in this lesson, that I will not comment upon, you find a sort of summary of all the things that we have said so far. So you have the heavy-tailed class, the long-tailed class, the subexponential class, and the fat-tailed class. If you want, instead of this movement from the bigger to the smaller class, we can also consider the opposite. So in a sense, we can start from the Pareto distribution that we consider the prototype of fat-tailed distribution. Then we define the class of fat-tailed distributions as the class of all the random variables of all distributions that in the tail somehow behave like a Pareto. Then we loosen this class, keeping some of the properties like the catastrophe principle, and we define this as the class of the sub-exponential random variables. We drop the catastrophe principle, but we keep the explosion principle, and we have the long-tailed class. Finally, we drop also the explosion principle, but we keep the properties related to the behavior of the tail and the moment generating function, defining the class of heavy-tailed distributions. So you can move in both directions if you want.